to go live. Perfect. Well, thank you everybody for attending. This is the live code walkthrough for the Superform competition. Here we have 3 members of the Superform team that will be going over the documentation and the code. Strongly recommend taking any notes if you need to. If you have any questions during the presentation, you can go ahead and ask questions in the top right of the Discord voice channel. You should see a comment button. And for the folks that are presenting, you can visit those to see the chats. Otherwise, we'll do Q&A towards the end, around 10-15 minutes or so of Q&A. Strongly recommend, again, please leverage that time to the best of your abilities, ask questions, because it's going to be one of your best opportunities to do so. But yeah, without further ado, I will hand it off to the team. So please, guys, feel free to take it away.
Cool. Thanks, Omar, and good morning, everybody. Excited to share Superform with you all. Before we get into it, we have a couple of people on our side on the call. I want to quickly introduce ourselves. I'll go first. My name is Vikram. I'm one of the co-founders at Superform. Been building in DeFi for the past few years. Most recently was co-managing the DeFi strategy at Block Tower. Sujit, do you want to introduce yourself next?
Hey guys, I'm Sujit. I'm a protocol dev at Superform. I've been doing DeFi since 2017 and been a smart contract dev for a while now.
Yeah. Hey guys, I'm Joao. I'm head of protocol at Superform. I've been coding Solidity since 2017 and I've been leading smart contract teams in the space since 2020. You can ask me any questions about the protocol, specifically about the periphery area, where I'll dive in shortly. Vikram now will start by introducing what we're building.
Cool. Yeah, let's dig into it. So what Superform is, and hopefully you guys can see the docs pulled up. Feel free to follow along as we're going through this. But Superform Protocol is a non-upgradable, non-custodial yield marketplace where protocols can permissionlessly list vaults to what we call forms, which are, think of them as vault adapters. They're currently built around the ERC 4626 standard. And for users, once that yield is listed on Superform, users can deposit and withdraw into it with any asset, any chain, multiple vaults in a single transaction, all that good stuff. So we're really lasered in on making the UX behind DeFi 10 times better. We're just looking to help protocols access liquidity cross-chain, get more users, and also for users to give them a more marketplace feel to how they're discovering, executing, and accessing yield right now. So the portion that we'll be talking about today on our code run through is going to be obviously the protocol, although there are other components in our docs that you guys can read up on more if you're interested. On the protocol side, we're EVM native. We're built on the 4626 standard, where we utilize infrastructure partners that are also only on EVMs, but we're just really excited about what's going on in the L1, L2 space, and we're focused on those ecosystems. Our Superform contracts can be split into 2 categories, core and periphery. Our core contracts contain logic to move liquidity and data across chains, and they also maintain a set of roles and addresses that are used in the protocol so that other parts of our architecture, like our keepers and our app, can properly index that information. And then our periphery contracts contain the main touch points for users to properly interact with the protocol, whether you're a protocol or you're just someone who's seeking out yield. We'll start by digging in on the core side of it. On the Superform core side, there's 2 main parts to this. First bit is cross-chain data. Cross-chain data is how we move data from chain to chain. Base state registry is the contract that other state registries inherit to move data from chain A to chain B. And broadcast registry is how we move data from one chain to all the chains that Superform is on. The way that these state registries work is by utilizing A and B implementations. At launch, we're going to be supporting Layer 0, Wormhole, and Hyperlane. Sujit will dive into more of the architecture decisions here and why we decided to set it up through multiple A and Bs and why we have multiple state registries even. On the cross-chain liquidity side, our core contract is liquidity handler. One of the main contracts is liquidity handler. Liquidity handler is the abstract contract, which is inherited by any contract in Superform which moves tokens, which is needed, because we're utilizing a bunch of bridges, which could then be using multiple dexes under the hood. The bridge validators that we've incorporated are for Socket and Li-Fi. Bridge validators validate that the transaction data that we're feeding in to those contracts are doing what's expected, and we add that another level of on-chain verification to make sure that that's doing what's expected. If we wanted to add more sources of liquidity, we'd have to add another bridge validator. DST Swapper is one of the contracts that inherits liquidity handler. DST Swapper is a contract that handles token-to-token swaps on the destination chain. If the vault, for example, is a very low liquidity underlying asset, and we'd have to find a more custom route to get that for the user. And then lastly, on the core side, Super Registry and Super RBAC had mentioned that Superform has a network of keepers that's processing transactions. We collect data on a lot of our vaults, a lot of things that's being done off-chain, and those two contracts help us in maintaining that we know what all of those things are. That's it for core. On the periphery side, there's two things that people interface with generally. One is if you're a protocol, you're looking to add yield to Superform. So you'd be adding yield to Superform Factory, and you'd be adding it to a form implementation that is listed on Superform Factory. And form implementations are things that the Superform Labs team can add on any chain to support more kinds of yield. At launch, we are just focused on the ERC 4626 standard. We have a base ERC 4626 implementation form, which is then inherited and used by ERC 4626 form. And then we have two experimental forms called 4626 time lock form, which is used for two-step withdrawals, which is on some on-chain time lock, and also KYC DAO form, which is experimental gated deposits for permissioned vaults. And protocols would simply be adding vaults to Superform Factory by providing a vault address and a form implementation ID. And whenever a vault is added, a Superform is created. And you can kind of think of that Superform as a pool on Uniswap, but that Superform then contains all of the tokens and all of the vault shares that are received to and from that vault before they go to the user. So that's on the protocol side. On the user side, the main way that users interact with Superform is through Superform Router. Superform Router, there's a bunch of different functions in there that allow for the optimized deposit and withdrawal into same chain, cross chain vaults, all that. And it gets information from Payment Helper to estimate the cost of cross chain transactions. Paymaster is our kind of think it's like a gas tank to actually manage those cross chain payments, but that's used by our cross chain infrastructure to it's used to subsidize the cost incurred by our cross-chain infrastructure. And whenever users deposit through Superform Router, and assuming that they don't retain the 4626, they decide to hold the 4626 through Superform so they can withdraw through their superpositions. They're minted a superposition, which is a variant of ERC 1155 that's also part of the scope of this audit. called ERC1155A, and that is effectively the cross-chain LP token receipt that we use in Superform. And all withdrawal requests go through superpositions. So yeah, the last bit of this here is emergency queue. This is purely a circuit breaker. The emergency admin can pause individual form implementations, and when paused, no deposits can go through Superform, but all withdrawals go through an emergency queue, and this emergency queue is processed on a case-by-case basis, and is purely used in an emergency scenario when we're doing in a war room or something and trying to figure out what the best next steps are. That's a high-level view of the protocol here. We'll be digging into Superform core next, and yeah, Sujit will run us through that. So I'll stop sharing my screen, and the reins are all yours, Sujit.
Thanks, Vic. I'll start with the Superform core stuff. Can you guys confirm, like, you could see the protocol diagram?
Yeah, we can see the protocol diagram. If anybody,
Okay.
just one quick thing. Sorry, Sujit. If anybody just saw the switch, it's not going to automatically switch. You have to click on the very left screen tab on your Discord view. So, but yeah, well, it's visible now.
Awesome. And if I switch to the code, is my VS Code visible as well?
Yep, we can see it.
Awesome. Okay, so Vikram introduced you guys to the overall protocol. Now I'll deep dive into the technicalities of the Superform core side. Before diving into cross-chain data and cross-chain liquidity, I'll introduce you to a simple contract called Superform, Super Registry, and Super RBAC. Both of these files are inside the settings folder in our core repo, in our main repo. And these two contracts basically have simple functionality. The Super RBAC contract is just a role-based access control for the entire protocol. It inherits OpenZeppelin's access control contracts, and it does a simple thing. It allows protocol admin to set different roles within the protocol, and then it allows other contracts to read these roles. There are two main roles. Apart from them, all the other roles are not that important. The protocol admin role and the emergency admin role are of greater significance because the protocol admin role is the one that can add all the other roles. It can revoke all the roles. It can add any complex or sensitive state changes within the protocol on the whole. And then emergency admin role is just for managing emergency situations. Like if there is something that's going wrong and we are notified through our alerting systems and stuff, then we use this emergency admin role to reduce the damage, like by pausing the form implementation or by broadcasting a specific stuff and things like that. All the other roles are pretty much inside the Super RBAC, like a setter and getter function. And then the protocol admin can set certain sensitive stuff across the entire protocol. So the Super RBAC contract is basically an RBAC contract inside for the entire protocol. And then Super Registry is kind of an index of addresses across the Superform protocol. The Superform protocol is a multi-chain protocol, so obviously it's going to be deployed across multiple networks. So it's just a registry of addresses deployed to all the different networks on a single chain. So, for example, from ETH, I can read what is the address of, for example, Superform factory on Polygon, what is the address of Superform factory on Avalanche, on Base, and stuff like that. Right now we are using Create2, but still at some cases, if even the Create2 assumptions fail, to support all the criteria, we have this Super Registry contract. So you can see these two contracts inside the settings folder. So I guess they have pretty similar functionalities of setter and getter functions. One difference is that Super RBAC has a broadcast functionality. So if you look at Superform's protocol, we have core contracts deployed across all the different networks. Like it's gonna be at the start be deployed to at least 7 different blockchains. So maintaining roles is on each of these network is gonna be difficult. So we have this experimental feature called revoke role super broadcast and stuff. Like from one single chain, you can revoke roles on all the other chains. So we do this by using Wormhole. Wormhole's broadcast functionality, which I'll explain a little bit more in depth on the cross-chain data folder part. So this functionality is basically to control RBAC from one single chain. So if you just revoke a role from ETH, it gets broadcasted and the role gets removed from all the different chains and stuff. But we don't want certain roles to be remote. These are more sensitive roles and we don't want to have more trust on the bridges and stuff since it's an experimental feature. So we prevent these 4 roles from being revoked through broadcast. So for revoking these 4 roles, the admin has to go to the specific contract deployed on that chain, and then it has to remove the role of given to the specific address or something. Apart from that, the broadcasted message enters the RBC contract through this function, state sync. If you look at state sync function on any of these contracts, then it's a point of entry for the cross-chain message. So state sync broadcast will be specifically called from broadcast state registry to revoke a role through broadcast functionality. So saying that, these are the 2 different setter and getter functions of the core contracts. The reason why these contracts are called core is that the user does not interact directly to these contracts. They just interact to these contracts through the periphery, or the core just interacts among themselves. So now we could dive into the cross-chain liquidity part. Before that, I'll want everyone to have a mental model of how Superform works. So in Superform, let's say if a user wants to deposit 100 USDC from ETH, like he has his USDC on ETH, and then he wants to go to Polygon and just deposit his 100 USDC to a vault. Let's say this vault is an example vault. So now he has to move his 100 USDC from ETH to Polygon. For that specific reason, the contracts inside the cross-chain liquidity folder helps. Like it takes the USDC from the user and it just uses a specific liquidity bridge, like whatever bridge that Socket and LeFi aggregates. And then it just moves the funds to a specific contract that we determine on the destination chain, we call it. So that's the part of cross-chain liquidity. And then cross-chain data is for moving the other part. To communicate the contract on the destination chain, what is the intent of this user who bridged this 100 USDC to deposit it to an example vault on Polygon. So that's the reason why we have these 2 different things. So, and then saying that, we use LeFi and Socket. So LeFi and Socket has an off-chain transaction data generation mechanism to move this 100 USDC to Polygon from ETH. So to verify if that backend service is working properly, to have some on-chain verification and stuff, we have this bridge validator. So we have an abstract bridge validator contract, which provides like what are the specific functionalities that we should have. We should have to validate the receiver. User cannot bridge to a different address and say like deposit 100 USDC to a vault on Polygon. That doesn't work because it has to be moved to specific contracts and stuff inside Superform protocol to execute that action on the destination chain. And then we have to validate the transaction data. We just do some basic validations, like if the destination chain ID is right, like user cannot bridge it to Avalanche and say like deposit 100 USDC to a vault on Polygon. That's a wrong transaction. So we just validate these kind of basic information like chain ID, receiver, and stuff inside the bridge validators. And we have a base validator that just gives in like some specific functions to get predominant information, like primary information, like amount, what is the receiver, and what is the destination chain ID and stuff. These bridge validator based contracts are then inherited by LeFi validator and Socket validator, 2 different validators for 2 different partners that we integrate with. So they just decode LeFi's sockets TX data that we generate off chain to recover those basic informations that I mentioned earlier to validate if these backend services are good and the transaction data given in by the user is valid. So if you just want to go through those implementation, just go in the cross-chain liquidity folder. You'll have a base bridge validator contract. That's an abstract contract. You have certain functions like validate receiver, validate TX data, decode amount in. One major problem with all these liquidity bridges is that we cannot decode the amount out. So let's say if I'm bridging 100 USDC from ETH to Polygon, I can only know the 100 USDC that I'm bridging. The amount that I will receive on the destination chain is not known. That's an infra drawback that we have. We solved it through a different mechanism that I'll explain later in cross-chain data folder. But that's one big drawback with these liquidity bridges. And then we have this LeFi validator inside the LeFi folder, and then we have a socket validator which just extends these base methods, and it just helps you get some valuable information from the bytes TX data. And then we have a liquidity handler contract, which is a pretty simple implementation. We generate the transaction data off chain. We know the bridge address, and then we just forward that transaction data to that bridge address, which moves the funds from our contract that inherits this liquidity handler to a different contract on any destination chain that LeFi and Socket supports. So LeFi and Socket are basically aggregators of multiple bridges. So you can use multiple bridges through LeFi and Socket. And then we have DST swapper. The reason why we have DST swapper is that in some cases, we cannot directly bridge to the underlying token. Let's say if the wall token is USDC and there is no liquidity for USDC on the source chain, then we just bridge whatever asset the user has to the destination chain, and then we swap it on the destination chain to the underlying of that specific vault. That's the reason why we have this intermediary contract, which forwards tokens to itself on the destination chain, and it just swaps the intermediary token to the vault underlying on the destination chain. Again, it does the same things like liquidity handler. The transaction data is generated off chain, and then it is validated through the bridge validator, and then it's just swapped directly using 1inch or 0x or Uniswap. And then being said that, that's how Superform core works to move the liquidity of the user, like the 100 USDC of the user from source chain to destination chain. Now the other part is like how we communicate to the contracts on the destination chain to do some action for the user. Basically, the action here is like deposit 100 USDC to a vault on Polygon. So for that purpose, we use the state registries. The reason why they are named state registries is that they store the cross-chain messages, and then they communicate with multiple contracts on that specific chain to just solve the user's action. And core state registry is the only point of communication between multiple chains. So if you want to communicate from one chain to another chain regarding a deposit or withdrawal, then all those communications should go through core state registry. The periphery contracts interact with core state registry, and then the core state registry is the one that interacts with the core state registry deployed on the different chain. So all these contracts are deployed across all the chains. So core state registry is going to be deployed across all the 7 different networks that we support initially, and it interacts with each other on all these different chains to establish a communication channel between networks. The core state registry is one such thing. It inherits base state registry. Again, it's an abstract contract, the base state registry. It just gives the ability to send and receive messages through all these message bridges. To give a more detailed explanation of how these things work, we use a multi-AMB approach. Superform doesn't use a single message bridge to send a message. We use a combination of message bridges, and we use a quorum requirement on the destination chain to process a message. So every user, let's say, if they want to say a destination chain contract to deposit 100 USDC for the user, they have to send that instruction through either 1 or 2 or 3 AMBs depending on the quorum requirements. right now, starting with, we have a quorum requirement of 1. So that means you have to send the payload through 1 AMB and the proof through at least 1 AMB. The proof is just a hash of the payload. So we just hash that payload and send it through 1 AMB. We just send the message through 1 AMB. And then on the destination side, we validate if these messages are not corrupted by the AMBs, and then we execute that message. So imagine like state registries communicate with each other, and then they use these arbitrary message bridges like layer 0, wormhole, and hyperlane to communicate between themselves. So diving into the code, all these stuff is inside the cross-chain data part. So we have two different base contracts. One is a base state registry that's used for one-to-one communication, where we just communicate from chain A to chain B. And there is a broadcast state registry, which specifically uses wormholes broadcasting functionality. The only difference is like it's a multicast functionality. It communicates from chain A to a lot of different chains in one single instance. We use this for experimental features that I mentioned earlier for revoking certain roles from one chain, for passing a form from one chain and stuff like that. It's not a part of the deposit and withdrawal process for the user. So this base state registry provides two basic functionalities for the contracts that wants to communicate cross-chain. One is like dispatch payload, which is used to send a message to a specific destination chain ID. This message can be arbitrary, so the state registry doesn't care about what's the message that it's sending and receiving. It's upon the periphery contract, and it's upon the destination chain contract to interpret the message and process the message. The dispatch payload functionality just has some sort of RBAC controls based on the extension contracts that it is inheriting. Apart from that, it just gives two functionalities. One is like sending message, the other one is like receiving message. And this dispatch payload functionality in turn interacts with these AMBs wrappers that I'll dive in right now. So we use three different bridges: wormhole, hyperlane, and layer 0, but all of them have different interfaces and stuff. So to wrap them into a common interface that can be used by the base state registry, we just use these contracts: hyperlane implementation, layer 0 implementation, and wormhole automatic relayer implementation, which has like basic dispatch payload modifier method again, which uses AMD specific functionality to send a payload across different chains and stuff. And then these extensions are the main contracts that inherit base state registry. We have core state registry that is the main point of communication between two different networks. And then we have a time lock state registry, which is a step above core state registry, which is specifically used by time lock forms and an experimental form that we are experimenting with. It's a special requirement form where withdrawals doesn't go through directly. It has to go through a waiting process. So during that waiting process, the intermediary state is stored in time lock state registry, and once it's processed, it just communicates with the source chain contract from here. And then we have a couple of utilities contract. One is quorum manager. It is for the message quorum that I explained while showing the AMD architecture here. So we need to have a quorum verification to prevent the protocol against AMD colluding and corrupting. So for that, we have this getter and setter functionality and an abstract contract called quorum manager. This abstract contract is inherited by super registry. So protocol admin sets the quorum for every destination chain ID on a chain ID. So it's like, let's say if you're sending a message from ETH to Polygon, we set like the quorum on Polygon for ETH message is 1. So it just validates if a message is sent through one payload AMB and one proof AMB. So that's the core functionality of quorum manager. So that's pretty much about the core contracts. I could dive a little bit more in depth for what core state registry does. So I have explained to you that during cross-chain liquidity, we have one drawback that we couldn't validate the amount out due to the infra drawback. So for solving that problem, we have this functionality called update deposit payload. So when you just bridge 100 USDC from ETH to Polygon, this functionality saves the destination contract, like if it received 99.5 USDC or 99.9 USDC and stuff like that, since we don't have any on-chain knowledge of the bridged amounts. So we use this functionality before a deposit goes through. So we update the payload and then we call process payload to deposit that funds to the vault on destination chain. And then if an acknowledgement is needed, we just send an acknowledgement back. Chain A to B is one path of communication, chain B to A is the other path, and for that we use the acknowledgements and stuff. And in case of withdrawals, we allow the user to specify settlements on different chains. Let's say if I withdraw from a vault on Polygon, I can settle to Polygon itself, or I can settle on any other different chain. Settling, I mean, like if you are withdrawing from a vault, you get the USDC back. You can either keep the USDC to your wallet on Polygon, or you can bridge it to any other different chain. User can specify this data during his withdrawal process when he initiates his withdrawal from ETH, or he can just allow Superform to update this TX data on fly. So that's also one reason why we have all these validations and stuff inside the liquidity data. Like these data are again generated by LeFi, but the user specifies certain criteria and we validate if the Superform generated data matches the user requirements and stuff like that. So that's pretty much about the core contracts. It basically does two things on a higher level. It moves the user's instruction from source chain to destination chain. For that, it uses the cross-chain data related contracts, and then it moves the user's liquidity from the source chain to destination chain. For that, it uses the cross-chain liquidity related contracts. Now, Joe will explain you guys how the core contracts are used by the periphery contracts and how all these helps the users to deposit into a vault and withdraw from a vault and stuff like that.
Yeah, thanks, Sujit. I believe you guys can see my screen now. And yeah, so taking on what Vikram started in the presentation in this diagram, and specifically on the periphery side, I remind yourselves that we have the supply side and the demand side. And focusing on the demand side, everything starts in Superform routers. So for each deposit or withdrawal function, the user has to provide an appropriate state request. These state requests are found in data types, so you can see them right here. And all deposits and withdrawals are also important to be divided in different decision points. So we can look at this decision tree to understand what entry point a user should be using. So we can think of single or multiple destination actions, actions with single or multiple vaults, or actions that just target the same chain, or actions that combine same chain with cross chain. There are different possibilities, and this image here summarizes them and the data structure that you should be using. You can find this image also in our Gitbook docs. And an important thing also to understand is that sometimes when we're performing a cross-chain action, specifically on the deposit case, and when we are in the destination side, the token that we are meant to supply to the vault is a low liquidity token. We are required to use destination swapper to perform a destination swap. And for withdrawal actions, users can choose to receive a different token than the one that they redeemed the vault from, but this token must go directly to the user. So there's no usage of destination swapper here. Some extra notes on these entry points. So a specific transaction can only be of a specific kind. So only deposits or only withdrawals. You cannot mix deposits or withdrawals. Also, you can only use a single external token to send from your EOA or contract. From the supply side, really what the user can do is to permissionlessly combine form implementations with vaults, and this is done via the creation of superforms. So forms are code implementations that adapt to the needs of a given vault, and end user can do this wrapping, but only Superform Labs can add new form implementations. By wrapping a vault into a form implementation, we get the Superform, which is assigned a unique ID, which is made up of the newly created form address, form ID, and chain ID. Finally, when the user completes a deposit, user gets minted a superposition, which is a type of 1155 that is modified by Superform Labs called 1155A. And on withdrawals, these superpositions are burned at the beginning of the transaction. Users can also, state in their state request where they want to retain the 4626 shares on the destination instead of being minted superpositions on source. And notice that by doing this, they cannot withdraw via Superform router. Only superpositions can be used to withdraw through Superform router. All right. So let's dive a bit in the general flow. There are some diagrams that can help you guys understand how the internal functions are called. You can find these on the README in the GitHub. But essentially, main steps that are relevant for all actions, in particular, either deposit, withdrawal, same chain, cross chain, is the validation of the input data by the user. So this validate Superform data here shows exactly that. And here we validate things like if it's same chain, we validate the existence of this Superform. Things like if the slippage is within the maximum accepted limit by the protocol, if amounts are not zero, if it's not paused in the case of deposits. I'll show later on why for withdrawals this check is not made, and receiver address if it's also set. The next step in all actions actually, is to forward tokens. We can view that here. So this token forwarding means receiving tokens from the sender and setting an allowance for the target contract that will receive them. In the case of same chain operations, the target contract is the Superform, and the tokens are transferred from the user. Finally, for same chain operations, there's the call to direct actions in the base form. The base form is the abstract token that all form implementations inherit from. And these are the two entry points which connect to the usage of internal implementation functions. For normal 466, these are the ones that are provided, these process functions, but any new implementation can take whatever form. Doesn't need to comply exactly to the usage of these internal functions. For the cases of direct deposits, for example, tokens are moved from router to this contract. Then we need to understand if a swap must be done before depositing to a vault. If the external token was different than the vault asset, that swap is performed, and then the actual collateral is supplied to the vault. And here we make a distinction whether the user wants to retain the first 66 shares or not. And if not, superpositions are minted at the end in via Superform router calling superpositions contract. For cross-chain operations, it's a similar flow. Looks more complicated, but bear with me, it's kind of similar. There's just a few extra steps. So there's the validation action also. You can see it here. It's pretty similar to the same chain operation. Tokens are also forwarded to this contract from the user, but the target contract is not the Superform, but rather the bridge that will operate the transfer of the tokens. This is for deposits, obviously. Next, it's important to validate the action that will transfer the tokens via the liquidity bridge. So we have this bridge validator, validate the X data function being called, which validates the user supplied parameters through this validate the X data function. And then the internal dispatch tokens function in liquidity handler takes care of sending this TX data to the appropriate bridge. In parallel, or in the next step, we have the dispatch AMB message internal function, and this is the next step. It arranges the message in this AMB message struct. You can also find this in data types and so. And the message consists of a header and a body. The header is an important piece that we save in through the usage of update TX history in superpositions, and this is important to mint or remint superpositions in cross-chain actions, either deposits or withdrawals if they fail. And then the final step is to send off this message via the selected AMBs through the dispatch payload call. So assuming that the liquidity and message have reached the destination side and everything has been handled appropriately in core state registry, as Sujit has explained, the call with update deposit and then processing the transaction. What core state registry will do is to call one of these two entry points, depending if it's a deposit or a withdrawal. So this calls internal functions that are present in the base format notation. For the cross-chain deposit is quite simple. The tokens that arrived on the destination core state registry are supplied to the Superform, and then there's an allowance increase to the vault, and the same flow as in the direct deposit. For cross-chain withdrawal, there's a redemption from the vault, and then if the user selected that they want to receive these tokens in some destination chain, it can be an arbitrary chain, doesn't need to be the source chain, and it can be a different token than the collateral that was redeemed here. Then there's a validation also of this TX data. So if len is different than 0, and they're dispatched. One important thing. So in case this operation fails because the vault, for some reason the redemption fails or some stuff here fails, then a message is sent back by the core state registry to super router to reissue the superpositions that were burnt. I'll go over that at the end of this presentation. Yeah. One last thing important to know in router. So let me open here Superform router. Is that all actions contain a forward payment call. So these actions only really work if users supply a subsidy for the action. So messaging, liquidity transfer, and keeper calls require this subsidy to be sent, and users can use a contract called payment helper to estimate the costs needed for these transactions. And I can look at payment helper here for an example. There's an estimate function depending on the type of state request struct that is used, and this provides a handy way to get the total amount of gas that the user should supply and to be forwarded to a paymaster contract. So for a payment call here, and then that goes off to paymaster. Paymaster receives this subsidy, and what it really does is it allows Superform Labs to withdraw these amounts to essentially any Superform registry ID. So the Superform registry contains it's a repository of IDs of contracts that exist in the system, and it allows these IDs, which are essentially related to the keepers, to be supplied with the tokens that are present here. These tokens can be supplied on the same chain, or rebalanced to is the cross-chain equivalent to this function. There's a third feature, which is the treat AMB, which allows to retry sending a message in case it got stuck, and this allows to reuse funds here to submit that transaction. Next, so on the supply side, as I talked in the beginning, we have this Superform factory. It allows people to add add forms, or mainly to suggest forms, but this addition is controlled by protocol admin, aka Superform Labs. And creating superforms, this is the part that is permissionless. Anyone can create a superform by adding a vault. And so the protocol admin can also pause form implementations, and this effectively acts as a circuit breaker to the protocol. And connected to this is an emergency action. So if the form implementations are paused, the whole flow is a little bit different. Deposits are restricted, and withdrawals can go to an emergency queue. I'll also show that in a moment. So this is the add form implementation function. It essentially ties an ID to the address of the newly allowed Superform implementation, and create Superform clones the form implementation. It creates a new Superform ID comprised of this new address, form implementation ID, and the chain ID where this is present. We can change the implementation status to pause, as I discussed. An important feature is that this is a broadcast-able function. So this pause status change can be sent off to all the other destinations via the broadcast message.
Sorry to interrupt real quick. Everybody, please mute your mics.
Can we
Yeah. Kodak and Darkart, please. I think both your mics are hot. Can you please mute your mic?
Can I continue?
I think I can mute manually. There we go. Okay. There. Sorry. Go ahead.
No problem. Yeah. So this function is broadcast-able. This pause status can be sent to all the other chains, and effectively, what this does. So I didn't dive in this specifically, but in our validation function here, let me see if I can grab it quickly. Yes, so this validation action for the pause only happens if it is deposited. Specifically, when the Superform implementations are paused, we want to let users withdraw through an emergency queue. So that's why this check is only done to deposits. And when the withdrawal requests hit the form, then the pause check is performed again, and any actions go to the emergency queue through this queue withdrawal. So essentially a keeper will act upon this emergency queue by calling execute queue withdrawal, this emergency admin, and it really calls this process emergency withdrawal function, which transfers the funds to the user. Finally, the superpositions inherit from 1155A, an opinionated variant of 1155. Yeah, and this manages the yield positions of the user. So Superform router, at the end of deposits, direct deposits, it can call mint single or mint batch. At the beginning of withdrawals, so we burn superpositions optimistically by calling burn single or burn batch. Only router can also call this. And state multisync and state sync, these are for the cross-chain actions. It validates the store TX history, which is the payload header, against the message that was sent from the destination back to source. And it understands if it's a deposit and it should mint superpositions, or if it's a failed withdrawal, for which case it should remint superpositions. Users can also split 1155s into ERC20s by calling the transmit functions. These are present if you consult the other repository. So 1155A can go here. And users can transmit their 1155s to ERC20s back and forth. this can only happen if ERC20 is registered to a Superform ID. So ERC20s can be registered to a Superform ID after 1155 for that ID has been created. So an important thing to notice about. Yeah, so this is a high-level overview of periphery. Vikram will now conclude with some last remarks about Superform, and then what this competition is about. Thanks.
Thanks, Joao. Let me share my screen again. Can you guys see that all right?
It's popping up slowly. Yep, it is visible.
Perfect. So everything that we just talked about was part of the SRC vendor of the SRC folder. Everything that is in the SRC vendor folder is out of scope, but everything else in there, that's the Superform protocol. Something else that we will not be focusing on particularly for the scope of the audit are exploits concerning the inappropriate behavior of keeper rules. So these are some of the option architecture rules that we support that both Sujit and Joao touched on a little bit, that just do upkeep, process transactions, manage some things in the protocol. While we're not going to be looking to validate any vulnerabilities found because of inappropriate behavior, we'll say that if they're behaving on things that they see on chain that are inappropriate, that's totally good and valid. And actually, I think that some of the most critical vulnerabilities we find could possibly be in how those permission rules are utilizing information that is on chain. So definitely helpful to understand how Superform works, but don't assume that Corsair registry processor is just going to stop processing payloads and that's going to be a griefing vector, right? That's not something that we're looking at. And then something else that's out of scope is prior findings, any audit report linked. We have two of those down here. Won't be looking at those. Some kind of like a cheat sheet, I guess, for things to focus on to find criticals. Our critical invariant is that superpositions minted on the source chain must always equal vault shares stored in the Superform, assuming that the user decides to not retain the 4626, which was a possibility that Joao mentioned in Superform router. If that invariant wasn't to hold, then users could drain superforms of all the vault shares, and that would be that's a problem. Another thing is that superpositions want to make sure that those can only be used to redeem from the appropriate vault it corresponds to on the right chain. So, I think Joao also mentioned that superposition IDs are formed by combining chain ID, form implementation ID, and the vault address. We want to make sure that those superposition IDs are unique and that when burning them, they can only be used to withdraw from the appropriate vault on the appropriate chain. So really just maintaining that one-to-one relationship, and both in terms of the amount and the vault that the superpositions are going to. And then last thing for finding bugs is this option architecture section is definitely, there's a lot going on here. And this rescue and disputer process, and how the processor rules and works with the updater, definitely would emphasize understanding this process, because the flow of how information moves from different states in the protocol and how errors can be thrown, something that would definitely be be worth diving into. Last thing to set up tests and stuff in the repo. Everything works with Foundry. Just remember to set up these, at the very least, these missing env variables. We've tested them using just normal Infura nodes, but have had better success using archive nodes. So whatever you guys see, have access to and can use. And then the rest of the test suite can be run through normal commands. You can also run Slither in the base repository just by using the Slither config JSON that's provided. And yeah, that's pretty much it. We're excited to hear about what you all think about our protocol. And yeah, we're here to answer questions now and in the Discord for the next couple of weeks. So Omar, however you wanted to do this Q&A portion,
no,
could take questions.
Yeah, but first of all, just wanted to thank you guys for presenting. Things is going to be very helpful. For everybody's sake, this is also recorded, so we will be posting this after the competition is live. So if anybody needs a reference, and apologies again for everybody, that's on me. I should have requested everybody to mute their microphones ahead of time. In the future, we'll make sure that doesn't happen. But just as a reminder for everybody, please make sure your microphones are muted. Whenever we hop into these walkthroughs, we want to show our protocol teams the utmost respect for taking the time out to do these walkthroughs. But yeah, I believe there is, if anybody has any questions, you're more than welcome to unmute and just have a chat with the team. Otherwise, please feel free to drop anything in the chat. You'll see a chat icon in the top right. I believe there are some already. Let's see. Morph asked a quick question. This might have been pertaining to some item, but he was asking, is the privilege used for the circuit breaker a multi-sig or an EOA?
Yeah, emergency admin is a 5 out of 5 multi-sig.
Excellent. If anybody else has questions, I feel like people might be a bit shy, but please, again, feel free to unmute. Otherwise, we'll leave it. We'll give some time. If you want to drop anything in chat, you're more than welcome to. But strongly recommend taking advantage of this while you have the team live. Otherwise, they'll be available afterwards inside of Superform General. And I'm sure folks want to look at the code first, and you'll develop more questions as we go. But if anybody has anything now, any clarifying questions that you'd like regarding scope, or even any items on documentation, etc., now's your time to speak.
Yeah. One quick question. When will be the repositories available for us to download so that we can start digging?
Yeah, so I can take that. So currently we have the launch time to be 20 p.m. UTC. So that's when the Cantina code repository will be live, and then the subsequent repositories as well. But yeah, Superform team, if you wanted to add anything, please feel free. Cool. Any other questions? Okay. Excellent. I think we are good to go then. We've just made time at 11 a.m. EST. Well, thank you everybody for attending. Again, really looking forward to everybody dropping some cool findings in the competition. One thing to note, we did just launch a new feature for commenting, so that will be available for you. We highly recommend using the Cantina code features as much as you can. If anything isn't intuitive, just let us know. We're a product-heavy team. You need new features, you tell us. We'll get things going. So thank you everybody for attending. Really excited for this competition kick off. And yeah, this will be recorded and posted once we're live. And yeah, everybody have a great rest of your day. Appreciate you all attending, and thank you Superform team again for taking the time out your day to walk us through the code.
Thanks guys. Happy hacking.
Yep, absolutely. Take care everybody.